Okay, so TVR is not here, but we will continue with some brief discussions before I start with my talk. We are going to start with a quiz. And this quiz is for the Bangalore Udgas and Udgis. The question is, what is this a picture of? Anybody? Anybody from Bangalore? It could be, it's kind of nondescript, could be anywhere. This is actually, sorry? Yeah, this is near my house. So I'm a Bangalorean. This is actually 100 feet road in Indiranagar. Yeah. So we live just off 12th Main Road, which is now a bustling street. Yes, I know. My mother and your dad, we discussed, both worked at ITI together. Rahul Dravid is also the side road, and I'm a little further down that same side road. This is my claim to fame, is that I used to play cricket with Rahul Dravid in the days of my youth. And then I let him go and do other things. Okay. So the reason I put this here is that I'm also part of the, I guess, IISc children family in a certain way. The Tejasvi Yadavs of physics. But Indiranagar was sort of intellectually infinitely far from IISc. So growing up, I actually had zero, perhaps, interest in science. This is around the same time, I believe, as TVR actually moved to IISc. It was roughly the time that I was born, and I lived there. Okay, so this is number one. Okay, so this is number two. So many of the IIT Kanpur people have disappeared, but for those who are remaining, this is a picture of the library of IIT Kanpur. That's a building there, taken from the physics department of IIT Kanpur, I think. That's in the faculty building. And I put up this picture because this is how TVR relates to my life. So the first time I heard about TVR was when I was assigned to work with Rajaram Nityananda one summer. And he gave me this theory of freezing. And I read this thing, I couldn't understand a word of it. So that was a failure. Then I went back to IIT and I said, everybody told me that this scaling theory of localization is a very important thing and I should read this. So I got this Reviews of Modern Physics. And for the first time in my life, I went to the library and every day I tried to read this Reviews of Modern Physics. And every day it would end up with me sleeping. And then you go around the corner, there's a nice tea shop. So I would go drink tea in that shop. And then at the end of about a month or two, I decided that if this was what being a theorist was, then this was not going to work for me. And so TVR's influence on my life via this famous paper was to convert me to an experimentalist. So that's who I am, with a few galis from Kanpur. Okay. So this is number three. This is again a relation to TVR. After many years, I now find myself at Columbia University. I dug up a picture from around 1960 of the physics building. So this would have been the building at the time that TVR was a grad student there. I asked many people where Luttinger's office was. I could not find exactly where Luttinger's office was. But what I found, this place, which looks nice now, used to be the old physics library. And when about 2 or 3 years after I came there, they tore it down and they now built this space. But when they tore it down, there were a lot of old books there. And I got a bunch of these books, which were some of them handwritten notes from Luttinger. For some reason, Brillouin, I don't know what Brillouin had to do with Columbia, but his notes were there, and so on. I don't have much interest in history, to be honest, but they're in my office if people like history. Now, I forget if it was Ravin or Senthil who told me about this article by TVR called Two Worlds. So this was fascinating. This is the first time I'd heard of it. And I read this article, and there were a few things in this article that really resonated with me in different ways. So this is from that article from TVR. One thing that really resonated with me, so this is TVR talking about how he applied to Columbia University to do graduate school. He says, again, without too much thought, but impelled by the belief that good graduate education and research in physics pointed outside India, support for scientific studies was most direct and abundant in US. I applied to many universities there. I thought this was exactly me at the time when I was graduating from IIT Kanpur. I was not exactly sure what I was going to do. So I found this guy, Ashwin, who had written a statement of purpose, and it worked well for him. So I copied it and I sent it off. And, you know, I kept proceeding along those directions and okay. The other thing which I found extremely interesting there, so TVR says I started graduate school at Columbia University in 1962. I spent the first summer there in the laboratory of Professor Madam C.S. Wu, who did a famous experiment on parity violation. And then he says that he gave up after 1 year and became a theorist. I was going to offer him, if he was here, he could come back, because now this lab of Madam Wu is my lab, and I actually have her office as well. So if ever TVR wants to come back and do experiments, the same lab, he can come and work.
Difficult experiments.
I do difficult experiments. Okay. So he may not be motivated. And this third thing, which actually resonated also with me a lot, he says, though theoretical particle physics was a big thing, I felt quite unsuitable temperamentally and mentally for it, and sleepwalked into solid state physics, an obscure activity then at Columbia. So I think now it is not an obscure activity, but when I still came to Columbia, I remember that we were treated as not quite second-class citizens, but as, okay, people to be tolerated. And there's a famous quote from Ravi, one of the department's big people, that I tell everybody that my department will not study the physics of dirt, anyway, okay. So that's all my entertainment part of the schedule, and this is now my scientific talk, and this is the title of my talk is Palladium Aluminum Iodide. So I'm going to tell you a story about a particular material, palladium aluminum iodide, which has this particular crystal structure. And something that I've realized over my life is that I really like to be a physicist for chemists and a chemist for physicists. This way I can stay out of both the faculty meetings and pretend that I don't belong there. Okay, so I like this compound. It's a very interesting compound, and I'll tell you a story of how this compound was made also. I'm going to talk about essentially 4 different papers, and I chose this one because it has some connections to TVR's work, although somewhat tangential. So there's 4 separate papers here. So apart from me, there are 2 people who really, faculty who contributed a lot to all of these works. One is my young theory colleague, Raquel. So usually when I have some vague idea, I'll go and mumble jumble. And my old theory colleagues, Boris Altshuler and Igor Alina, would just kick me out. They'd be like, get away from here. But Raquel is very kind, and she's untenured, so she cannot kick me out. So she tolerates me and becomes my co-author. And the other person is a really wonderful chemist. So when I first saw Roy, I thought he was a Bengali, but he's not a Bengali. He's from Canada. He's a French Canadian, and this is pronounced wow, something like that. But he's a chemist, and a good chemist is worth their weight in gold or maybe rhodium or something. So there are all these papers. So all the blue ones are Zavs. Zavs, how we call them, Zavs people. The red one are my people, and green ones are Raquel's people. So how this compound came about was Zav, who was also untenured at the time, so he was more amenable to listening to me. I went to him one day and said, look, we have all this graphene, it's a semiconductor, it's a semi-metal, we have semiconductors, we have superconductors. How come we don't have a peelable version of gold? I just want gold, just a metal, but I want a 2D peelable version of gold. And he said, okay, I'm going to go make something. And this is the best thing that he came up with. It's not gold, but palladium is pretty much like gold. And his trick, which he now uses to great effect, is to dimensionally reduce all of these compounds by including halogens. So what this compound is it's palladium, that's a metal. This is a very important layer, I'll tell you more about it. This is palladium aluminum, and then on top and bottom you have iodine. And the iodine basically separates each layer from each other layer. So this is a 2-dimensional van der Waals metal. Very good. So let me get to the results. And the results are very straightforward to tell you, but then I'll tell you a story about the results. That hopefully is interesting. So what we did, and this is the way things work in my lab, is Zav makes something and then he gives it to my student and I say, go on, put it in the STM and measure whatever it is. I don't care what it is, but just measure it. And this was a metal. And what my student at the time, Simon, did was he went and with STM, you can do local spectroscopy. And when you do local spectroscopy, what he saw was that there was a defect in this metal. And if you look around this defect, you saw something that looked like a bound state here. So here there's a bound state. If I measure at this energy in space, you see it has a beautiful structure in space. This is a bona fide bound state that is sitting in a metal. Then here is another one. This is at a different energy. This has a different symmetry than this one. And when I saw this, I've done STM now for quite a few years. I scratched my head and I said, never seen anything like this in a metal, like a bound state in a metal. How is this happening? And then Mike Cromie, who was my favorite STM person, visited me. I said, Mike, have you ever seen anything like this? He said, never seen anything like this. I said, this must be interesting. We have to study this more. So this is the story I want to tell you about. I want to tell you about why it is that you have bound states in this metal. Okay? And to begin the story, let me set the stage by saying, in general, in physics, we are very used to energy diagrams that look like this. You have some particular single particle potential, and this gives rise to energy states. They can be bound states like this, discrete bound states. And they can also be delocalized states, so continuum of states, hydrogen atoms, so many other different cases. And here, when I talk about delocalized, I mean a wave function that cannot be normalized, and localized is a wave function that can be normalized. Okay? Now, usually in quantum mechanics, localized and delocalized states do not occur at the same energy. The energies of the localized states are distinct from the delocalized states. But of course, we've learned that in cases weak localization, things like this, there are ways in which you can actually have this. Now, here is now the second quiz. I have another quiz for you. So this is for all the theorists. So here is a potential. This form of this potential looks like this. It's minus V naught e to the blah, 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 looks like this. So it's an exponential function like this. And this is zero, if you wish, zero of potential. And this came from a very nice paper published by some folks from BARC Mumbai. It's just single particle physics solving the Schrodinger equation. And I want to ask you, where are the bound states and where are the continuum of states for this particular potential? Anybody wants to guess? Attractive potential.
Unbounded.
Unbounded going off to infinity.
All continuum states.
Okay. So the answer is that indeed there are continuum states for E greater than 0. There are continuum states for E less than 0 as well. But at these very particular energies, E equal to blah, 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 it turns out that there are localized states, localized meaning that they're normalizable states that occur above this potential, right? Above the maximum of this potential. And I'm going to give you a picture of one of these states. So this is one of these states. So it's a normalizable state, but it lives in above the maximum of the potential.
Virtual bound.
Yes, yeah. So in other places, yeah, like nuclear physics also, you see these kinds of things. But this is an example.
Based on the existence. Like if you had a tunnel barrier, for example, you could create, if you had a well and a tunnel barrier. Sorry. I'm saying if you had a well, where you would have normally had a bound state, but a tunnel barrier, and then it goes off this infinity, then there's a weak tunneling between this bound state and then the continuum which is outside.
But those live in below the maximum of the potential energy.
That's true.
So here, this lives above the maximum of the potential energy.
It's kind of a bit like anti-localized bound state.
Yeah.
What we call anti-bound, like near the top of the band.
I see.
Something like that.
I see. Okay. So it turns out that this is being discussed all the way back in 1929. There is this paper from Neumann and Wigner, which is in German, and I put the English translation here, but let's not worry about this. what they did in this paper is that they considered this particular potential, which is a more complicated potential, and they showed that this particular function sine r cubed by r squared is a solution to this potential, which is similarly a sort of bound state. And this bound state, it lives within a continuum of extended states. So it lives at the same energy as, or within those band of energies. Okay, so these are all sort of, if you wish, mathematical curiosities. The one area of physics where this is not a mathematical, yes, it's power law bound in this particular case. Okay, okay. Yes, okay, I'm just saying.
In all these examples, the potential is unbounded from below?
Yes.
Only in these two?
No, in all these, it's unbounded from below, and there's some interesting interference argument also you can make about how you can get these things. Okay, so this state, these bound states in a continuum was sort of a mathematical curiosity until the era of photonics. So in photonics, as you know, if you look at the Maxwell equations, this is basically like Schrodinger equation, and you can create basically arbitrary potentials for the photons by making holes in your dielectric. And this turns out, I just want to put this there just to show you that this is kind of a big field in this photonics to make these bound states that live at the same energy as the continuum of photonic states. So there's various different ways of doing it. Marin Soljacic, John Oplas, they're sort of big people, done lots of different works in this. But let's now come to solids, which we know and love, and let's ask how, if I put a defect in a solid, then what are the options for what you normally get? So one option, if I take a solid which has a band, a non-interacting electron band, and I put in a point defect, and this defect has a potential energy which can trap an electron, it's possible that this state lives outside the band. And so then you have some sharply localized state, and then its energy is outside the band. This, of course, we know very well. This is how all of our electronics works. These are bound states in semiconductors. And such things have been imaged in STM many times. I just give you one example. This is manganese in gallium arsenide. Okay? If you take a metal and you put a defect, and this defect is not so strong as to pull this state out of the band, then what you should do in order to properly describe the effect of this defect is to construct states that are just linear combinations of the block states. That's what you would do. And in general, if I go ahead and I see what kinds of perturbations this defect does to the local density of states, what it will do is it will take your block states and it will break their translational symmetry. It will change the wave function locally around the defect. This is something also very well known to STM people. We have a technique called quasiparticle interference to analyze these kinds of phenomena, and so on and so forth. But now the question that I want to ask is, can we make a sharply localized state in a metal that lives inside the metallic band? Okay? And the answer is yes, you can do that. And there are actually multiple ways of doing that, but the way that I want to talk about is using geometrically frustrated lattices. Right? And the example I'm going to give you is the most well-known example of these types of crystal motifs, which is the Kagome lattice. Right? So here is the Kagome lattice. And the property of the Kagome lattice is that it features geometric frustration for hopping of electrons. And so this is a very nice cartoon. What this cartoon is supposed to say is, if we construct a wave function for electrons that live on this hypothetical Kagome lattice, and we only allow nearest neighbor hopping, there's no interactions. And if we construct a wave function that has the following phase structure, so it looks like here, it looks minus, plus, minus, plus, minus, plus. And we ask what's going to happen to this wave function as I evolve it with a Hamiltonian. You can consider, for example, this particular red point, and you can ask what the hopping is of this state to this red point. And the answer is 0, because this guy hops with a negative sign, and this guy hops with a positive sign. No matter what the sign of this guy is, the net hopping is 0, okay? And so you can figure that that's the case for all of these sites. And therefore, this state is actually an eigenstate of the Hamiltonian, which is wonderful, right? So even though this has translational invariance, even though the states are block states, I have another basis in which I can write the eigenstates of the Hamiltonian, and this is a purely local basis, if you wish. And these kinds of states are called compact localized states. And as you might guess, immediate consequence of this, since I can write wave functions that look like this that are localized in space, that this has to be a flat band. And that also follows. Okay, so a couple of interesting properties of these states that are relevant to my talk. One is that these states are not actually orthogonal to each other, even though they are localized in space. You can easily see that if I translate this guy to the next lattice site, it has an overlap there, which is non-zero. Another thing is you can always construct larger versions of these compact localized states by forming linear combinations of these compact localized states that don't live on one of these rings. For example, let me give you an example of this. If I construct a state where I take one of these compact localized states, I take another one of these compact localized states, and I add them together with opposite phase, then exactly in the center, they will cancel, and they'll give me a hole in the center. And you can see where I'm going with this. If I have a defect you can think about as a point potential. The point potential is going to infinity. You want to try to avoid that state. You can create a local eigenstate of the Hamiltonian that lives around this defect that completely avoids this site. But it's an eigenstate of the Hamiltonian. You can also construct a state if you want to enhance the intensity at the defect site. What you do is you add these same two localized wave functions, but you add them together with the same phase, then they have twice the amplitude. That's also an eigenstate of the Hamiltonian. And I can construct many, many such states if I wish. Okay? So with this, now I think I've given you basically the punchline of how it is that I'm going to create localized states in my material. So now let me come to the actual material and convince you that it's an example of this kind of geometrically frustrated lattice. Okay, so this is palladium aluminum iodide. And the important part of palladium aluminum iodide is this palladium aluminum plane. So you can forget about all of the rest as far as the low energy physics goes. And what this low energy physics comes from is, whoops. Okay, I think I'm ending up in an India problem. Okay, there we go. So you have a palladium orbital, two palladium d orbitals here in the middle site there. And these two palladium orbitals are talking to the other palladiums via the aluminum Pz orbitals that look like this. And this is once again an example of a geometrically frustrated lattice. So this one is called a decorated checkerboard lattice. And the way you see this is to do the same thing. You can see that since I have d orbitals here, they have definite phases. And the Pz orbital of aluminum also has definite phase up and down. And if you do the same sort of analysis that you do for the Kagome lattice, I won't go through this here in detail. You can convince yourself that this is also a geometrically frustrated lattice. All right. The decorated checkerboard is a close brother or cousin of the more famous Lieb lattice. So here's the Lieb lattice. This is the electronic structure of the Lieb lattice, which is also geometrically frustrated, has a flat band that looks like that. The decorated checkerboard also has a flat band like this, together with these Dirac bands that also appear. And of course, the real material has further hoppings. It's not just limited to nearest neighbor hopping. And so if you actually do RPES on this, so this is the RPES measurement, you have to squint to really recognize what this flat band is. But this is kind of the state of the art. In all of these Kagome materials and in this material, the flat band is not really super flat, but it has a bandwidth that is much smaller by about an order of magnitude than the intrinsic T that goes into the nearest neighbor hopping. Okay, so this material has a flat band like this, which comes from this geometric interference. And then the next step is to ask, what does a compact localized state, one of these eigenstates in real space, look like in this material? And let me show you how that thing works. So here is the basic motif. These are the d orbitals on the palladium, the p orbitals on the aluminum. And in order to form a compact localized state, what you have to do is you have to take 4 of these, and you have to add them in this particular phase relationship. So if this guy has a particular phase, I have to rotate that phase by pi over 2, pi over 2, pi over 2, and go around in a circle like this. And if you add this all together, then the wave function has amplitude only on the palladium sites and 0 amplitude on all the aluminum sites. Okay, so this is kind of going quickly, but if you work it out, it's not that hard to figure out that it's going to work like this. So this is one compact localized state. And now what I want to do is I want to create a defect in this lattice. And now I have to avoid a site, as I told you, when I create a defect. And in order to do that, I have to take 4 of these compact localized states. So here is one, here is one, here is one, here is one. And pay attention to the phases, relative phases of these 4 compact localized states. And if I superpose this one and this one, like this, I add these together, then I get, come on, the white here means 0, and then I superpose these, these 2 together, I add them together, and eventually, I get a complete cancellation on this particular site. So it's very much like the Kagome lattice, except it's different since it's a decorated checkerboard. And what you'll get is you'll get an eigenstate of the Hamiltonian that lives around a defect. And this eigenstate has a very particular symmetry. You can see that it has a D-wave-like symmetry. It has nodes along these 2 directions and maxima along the other direction. Yeah, please. That's right. Yeah. So within a reasonable bound, and I'll show you a little bit, we explored this just in tight binding. You can ask how much you can modify it and keep these properties the same. And yeah. Okay, so come on now. Okay. All right. All right, so now I come back to the actual experiment, and Senthil is already done with me, so he's going away, as is Mandar. Bye, Senthil, Mandar. And so what this defect is it's a vacancy in the palladium site, and this is something we can confirm with DFT that this is a vacancy. And now that you have understood the physics of this bound state, you can understand the structure of this. This is precisely the structure of that compact localized state that avoids the impurity site. That's this guy. And there is a second one where all the dangling bonds from the sides get together and are enhanced at the impurity site. And that's at a higher energy, as you might expect. And that is precisely this site. Right? So that's how we understand these states. These are actually compact localized states, which you are visualizing because you put in a defect into a geometrically frustrated lattice. All right, so we'll come to that. And now, in answer to your question, Kedar, so what we did is we played with this in tight binding. So in tight binding, you can sort of make a model of this. You can put a defect on a particular site, and then you can vary various things, like you can vary hoppings, nearest neighbor hoppings. Okay, this is really frustrating. So once again, this is sort of the phase structure of these 2 bound states. There's one which has nodes. That's this one that I showed you earlier. And there is another one that you can construct, which is enhanced at the center and has a radial node, exactly like what we see in the experiment. Yeah, so that's precisely what we see. Yeah. And so there's only 2. So then you can sort of play with tight binding, and we can ask at what point does this whole thing fall apart. And it turns out that you have to really modify the hoppings by quite a lot in order to completely delocalize these states. So up to a very reasonable range of hopping parameters, they stay localized. The localization length increases, but they still stay localized. In experiment, they're very localized. We can measure this localization length. It's within 2 lattice constants. Okay, so how much time do I have? Who's keeping track of time? 5 minutes. Okay, life is bad. So we'll skip all this stuff. They also behave like molecules. You can get them to interact with each other. But since Subir said the magic word condo, I'll talk about condo. So the next question I asked Zav is, I said, wouldn't it be wonderful if you can occupy this bound state? This bound state was above the Fermi level, it was an unoccupied state. I said if it was an occupied state, then this would be a magnificent thing because you could now occupy it with an electron, and it would be a local spin 1/2 moment. It could show the Kondo effect, but this would be a very special kind of localized moment because it doesn't really come from a localized orbital. It comes from a linear combination of all the block states conspiring together to give you a local moment. And Zav said, I'm doing it. And he made it. So what you can do is you can put in substituents, titanium and iron that do this. They drag this bound state below the Fermi level. And when you do this, indeed, you can see the Kondo effect. Right? So here you can see very nicely beautiful Kondo resonance at the Fermi level, very sharp Kondo resonance. And how do we know that this Kondo effect is really related to the bound state in the continuum? What we can do is we can actually image this Kondo resonance in space. And when we image this Kondo resonance in space, we get exactly the shape of the bound state in the continuum. Okay, so let me show you another picture of this. So here's a picture. This picture, which is indistinguishable from the bound state in the continuum, is taken exactly on the Kondo resonance. So there, exactly at the Kondo resonance, you can see this thing. Not only this, we can actually image both the singly occupied and the doubly occupied states. If you go below the Fermi level, you can image the singly occupied state. If you can go above the Fermi level, sorry, I'm jumping a little bit. Okay. We can image both the singly occupied and doubly occupied state. They live below the Fermi level, above the Fermi level. We know the Kondo resonance width. We can estimate the J in the Kondo from this. And we can estimate the coupling to the other flat band states by sticking it into the formula. And one of the very interesting aspects of the Kondo in this particular material is because of the way these states are constructed, these bound states in the continuum only talk to the other bound states in the continuum. They don't talk to the Dirac bands. They're orthogonal to the Dirac bands. And so if you measure transport, in a transport measurement, you actually won't see the Kondo upturn because they're completely unaffected by this scattering. But if you do a spectroscopy experiment like what we do, you can actually see this. Okay, so that is Kondo. And then finally, I wanted to make, okay, so there's many interesting stories of this. You can put two of these together. You can get sort of singlet, triplet Kondo. You can make a chain of these. You can make a chain, et cetera, But what I want to tell you in the last 1 minute and 21 seconds is a connection to localization. So this is an exfoliatable metal. And so this is a perfect material where we can really look at localization physics by simply taking the material and peeling it and taking it down to 1 layer in thickness, right? And this is quite different from all the previous studies of 2D metal films. Of course, there are many beautiful experiments on semiconductors where you really have single crystal semiconductors. We heard a lot of that earlier in this conference. But if you look at 2D metal films where signatures of weak localization and so on have been seen, these have all been sort of polycrystal or amorphous materials. Here is an example where we can take this material, we can just use Scotch tape exfoliation, and we can go down to 1 layer in thickness. But now, because it's exfoliatable, because we can go down and really measure this, we can really measure not only transport properties, but we can also measure spectroscopic properties in this 2-dimensional limit. And we see something quite interesting. It's something that we still haven't digested yet. It will appear in PRL without much explanation. If you measure the spectrum of the 2-dimensional film of this compound versus the bulk, you can immediately see that the spectrum looks completely different. It has all these peaks in the spectrum everywhere, as you might expect if you have localized states. You can go around in space and you can follow the local density of states everywhere in space. And you'll indeed see that there's all these localized states that live in different parts in space. And there's all these spectra, local density of states, which tell you how these states evolve at different points in space and energy. And I don't quite know what to do with this. I feel like there ought to be something good to do with this. But a lot of you are experts, so maybe you will tell me what to do. So I think my time is up, so this is a good place to stop and take other questions.
Abhay. Thanks for a very entertaining talk. So I'll suggest something to do with this. Since we are talking about weak localization, I think in a controlled way, if we can understand interactions, I know there were the earlier work which said interactions and disorder will also localize. But if you have interactions near Mott insulators, then there are predictions that interactions and disorder can, in that situation, can delocalize. So I think that kind of thing would be very useful to study, since you have these systems, you can put these defects, and maybe you can gate them, so you can change the screening.
Yeah, gating is tough because these are very good metals.
Okay, but let's say some
yeah,
other...
but the screening we can change. In fact, for this experiment, we put it on a gold substrate to really screen out interactions as much as possible. But we can change that. We don't have to put it on this gold.
Right.
Yeah,
So
that's
I think
an
that
interesting
question
suggestion.
is still open.
Okay.
Just a question about a clarification. When the modes are combined to miss a site or miss a group of sites, what's making them do that? What is the actual impurity?
In which case, sorry?
In the decorated, in the material, what is the defect? You just said defect.
In this two-dimensional case?
Yes,
or?
yes.
There's no additional defect.
No, in the earlier one. The previous
so
one.
First, the vacancy produces states that are
So
vacancy.
it's literally a vacancy?
Yeah, whole.
Literally.
Literally
Okay.
a
Not a different atom.
That
That
when
was
you
the
put,
other thing.
that gives you condo when you put it. It's okay, we can hear you.
Should two of these states have some funny non-local interaction between them?
It's not non-local. They have to really be close enough that their wave functions overlap, and then they produce bonding and anti-bonding states. But they don't work exactly like molecules. It works on the basis of the phase relationships between these things, which is the bonding and which one is lower and higher in energy. Is different from molecules in an interesting way.
But it's not they have to be very close to each other?
Yeah, they have to, it's like a hydrogen
they're
atom.
built out of these extended states then.
Yeah, even though they're built out of extended states, they're really very sharply localized. So you have to bring them within touching distance to get some interaction. Yeah.
Is it a charge defect actually? If this is singly occupied, is it a charge defect? And then I'm just thinking about Friedel oscillations and the observation of if there is a charge defect. So as you know, if there is a charge defect in a conduction band, then there are Friedel oscillations or charges, right? So do you see?
Yeah. So I didn't bring that data here. We do see that, and we can measure that at different energies, these scattering states. And we can use that to diagnose the band.
Is it possible to?
But these are not really charge defects. If you do your chemistry, then none of it makes any sense. So palladium, aluminum, iodine, if you do the valence count, doesn't make any sense. It's what chemists call a gold bond.
Okay. Thank you.
The fact that you can make these localized states and make lines, I mean, that's fascinating, powerful. Palladium itself is a superconductor. And so if you can make this, by hydrogen, whatever, into a superconductor, then you could attack the problem of heavy fermion, localized impurity in superconductor.
Yeah, well, I don't know about heavy fermions, but yes, we are trying under pressure to see if it goes superconducting, absorbing hydrogen, various things.
Is there any further question? Okay, if there are no questions, let's thank. Yes, please.
I'm going to go one up on Subir. You grew up in different localities of Bangalore. I grew up in the fourth class Janagar third. The third class Janagar third floor, 100 feet away from me was Princeton. Here, critical itself. And then one more point was B.S. Chandrasekhar's house.
Okay. Fourth block Jayanagar people were the elite people of Bangalore. So you're one of the elites. Okay.
Okay, let's thank Abhay for a wonderful talk.
Thank you.